Okay, hi everyone. It's great to open this semester's gravity seminar. And today we're lucky to have Vitor Cardoso from Niels Bohr Institute and IST Lisbon. And he will tell us about the sound of black holes. Please, Vitor.
Thank you, Shahar. First of all, thank you for the invitation. I'm really thrilled to be here speaking to you. I will talk about a subject on which I've been working for the past 2 decades, but which has really seen a lot of developments in the last few years, in the last 4 years, and we're really at a celebration stage. This year we mark the 10th anniversary of gravitational wave astronomy. So I thought it was that the time was ripe to talk about this. And I'll basically talk about something that's only possible with gravitational wave physics, and that's gravitational wave spectroscopy, to understand the proper vibration modes of black holes. This is an old subject at the theory level. And you know, sometimes you can do a lot of things, or you think you can do a lot of things before you have data. Once data comes in, all the story changes, and I hope to tell you a little bit about it. Now, the reason why we want to know about black hole spectroscopy or about gravity in the strong field regime, it's basically twofold. The first, I think it's obvious, our understanding of physics is certainly not complete. We know that there's some dark ingredient out there. The standard model cannot be the final word, or at least we have robust evidence for that, and it comes from a number of observations, galaxy interactions, rotation curves of galaxies, gravitational lensing. What seems to be there attracting matter doesn't seem to be there when we look out with telescopes. With the luminosity doesn't match the amount of matter. So there's something missing in our understanding of the standard model, okay? But there's also, and I think this might even be more serious, there's certainly something missing in our understanding of the description, the theoretical description of the gravitational interaction. And that issue becomes more serious. In fact, it becomes tragic in the strong field regime of gravity, in particular, when you start forming trapped surfaces or black holes, okay? This might happen at the beginning of the universe, but I will focus on the issue that I think is more kind of interesting because it happens trillions of times, and that's in the interior of all black holes. And there's a very nice, simple result by Roger Penrose that says, whenever you form a trapped surface, or if you wish, whenever you form a black hole, then something wrong goes on or goes in the interior of black holes, or something wrong goes with the understanding of how matter behaves, okay? Either negative local energy occurs somewhere in the universe, or Einstein's equations are violated, or even our concept of space-time needs to give way to something else. Okay, so to me, these are the two pillars that tell us we really need to understand black holes, and by understanding means we need to collect data and make sure that all the data is in conformity with our expectations. Fortunately, for black holes, our task is somewhat simplified, and the reason is what's called the uniqueness result, or the no-hair theorem, which states that in vacuum, so in the absence of all matter, then the exterior of a black hole space-time is very simple and totally described by only two parameters: the mass, m, and the spin, the angular momentum per unit mass, a. I'm setting Newton's constant and the speed of light to 1. By the way, please interrupt me. It would be awesome if this is really just an informal conversation. So feel free to just open the microphone and talk to me. And this really is an amazing kind of result of the mathematical content of the field equations, okay? You may argue, and I think you should by now, that there's strong assumptions behind, namely that it's vacuum and certainly our universe is not vacuum, or I wouldn't be here talking to you. But still, we think that the behavior of black holes, as far as gravitational waves are concerned, is mostly dictated by regions where to a good extent there's vacuum. So this is an impressive result and tells you that you don't need to really worry so much about all the astrophysical uncertainties with what happens in the real universe. So it's kind of interesting that, having known this, there was a talk by Subramanian Chandrasekhar in Hamburg, where I just came from, in 1986. And he said the following remarkable thing, that a confirmation of the metric of the curved space and the geometry I just showed, or some aspect of it, cannot even be contemplated in the foreseeable future. It's kind of a remarkable statement. And we could discuss why it's so remarkable. And I want to tell you what changed since this 1986 date. And what changed, of course, is that we have the ability to detect gravitational waves. This is the first event seen in 2 detectors. We have robust evidence that it refers to the coalescence of 2 black holes. And it's kind of a simple exercise to show that something here must be moving very close to the speed of light, and something here must be really, really compact. Okay, the mass must be stuck in a really, really small region. And I'm going to hopefully provide some evidence that this is a black hole. Now, to some extent, and this is something that I often end up discussing with colleagues, to some extent, discussing whether or not we're looking at black holes in that LIGO-Virgo plot is not too dissimilar from discussing this image, okay? And when you look at this, we have, well, I have 50 years of experience of being a human on the planet. So you kind of know that this is something that resembles a planet. You see some storms, you see some eddy currents here. So the atmosphere seems to be turbulent. In fact, there's a very, very interesting turbulence going on in this surface. And you might even know that this refers to Jupiter, okay? Whether or not it's really Jupiter, well, does it really have the number of mountains that Jupiter has, exactly the same atmosphere? To some extent, is irrelevant, okay? But that's not quite the case with black holes, because the defining feature is that they have an horizon, okay? And so a sink, it's a hole, it's where time stops, it's a causal boundary in the universe. And so it's really not a question of detail. It's, I think, a fundamental issue to know and to quantify the evidence that you have for black holes and horizons in the universe. So, usually the evidence that you tell your students is it's dark and massive. We know nothing else that behaves in this way, so it has to be a black hole. And I will discuss how to go beyond that, okay? So my purpose is to answer 2 questions. First, are we really looking at black holes when we look at gravitational wave data? And if we are, how can we quantify that these are black holes that belong to that simple 2-parameter family that we call the Kerr family? Can we constrain alternatives? There's many different ways we can do this. Okay, I'm going to focus on one. I'm going to focus on the characteristic modes of vibration of black holes. And that's more or less the same problem as trying to understand the sound of a bell, or trying to infer the shape of an object when you listen to its sound. Okay, so it's really what we're doing here. It's a very simple exercise. At the formal level, the way it works, it's more or less clear. We have a good understanding of this, right? So we have the coalescence of 2 compact objects. Let me assume they are black holes. They're emitting gravitational waves. And if you use energy conservation, then they need to come closer together as time goes by. And the end state, if it's a black hole, and if it's a stationary end state, which is one assumption, okay? But if it's a stationary end state, then it has to belong to that family. So here, time runs horizontally. So at very late times, we're looking at a Kerr black hole. If you do the exercise of going slightly backwards in time, well, then you should find something that looks like a black hole, looks like a Kerr black hole, okay? So the idea is to take the Einstein field equations and fluctuate them around a Kerr black hole. It's exactly what we do when we want to understand sound waves of anything, right? We just linearize against an average pressure and density. When you do that in general relativity, so you fluctuate either the metric components or some Newman-Penrose quantities, it doesn't really matter if you don't know the details, but you'll always end up with the following result. The angular variables, because there's a lot of symmetry in the stationary solution, the angular variables can be separated and decoupled, and you end up with a partial differential equation that looks like a wave equation, this equation over here, okay? There's a master function psi, you can think of it as the Schrodinger equation, a master function psi that encapsulates some combination of the metric fluctuations. There's a non-trivial effective potential V, okay? If it was Minkowski, the potential would vanish everywhere. So this really would be a wave equation in Minkowski. And then there's a source term that tells you what exactly is disturbing the black hole. Maybe it's my hand, I'm waving close to the black hole. Then this source would be some sinusoidal function of time, okay? So we have very robust tools to analyze this equation. We can do, for example, a Fourier transform. So we get rid of the time dependence, and you end up with something that looks like this. Formally, an operator that you can solve, formally at least, that you can invert to find the Fourier transform small psi of that master function, okay? It's exactly what you do if you want to analyze the vibrations of a piano string with fixed ends. Now, when you look at black holes, you need to impose, or any physical problem, you need to impose boundary conditions. And once you do that, your Green's function is totally defined. All the solutions to your problem are defined, okay? When you're dealing with piano strings or the Schrodinger equation, then the poles of this resolvent, the numbers, the frequencies that make this equal to zero, right? They are poles in your Green's function. We call them quasi-normal modes. If it's a string, we call them normal because the problem truly is stationary. They are real numbers, and you see, you really just get an harmonic time dependence. But a string is conservative, a string with fixed ends. A black hole is not. Waves must be able to traverse the horizon and travel to infinity, so you know that intrinsically the system is non-conservative, right? And in fact, when you solve for these frequencies omega by imposing the correct boundary conditions, you're going to end up with numbers, and I'm going to show you, which are complex. They lie in the complex plane, okay? Good. Now, this is kind of more or less trivial. When you invert this function small psi to get the real master function psi, if you think about integration in the complex domain, you usually use, contour integration. And these numbers, these poles, they contribute to that integral as a residue, okay? But the time dependence is this. So what you can see immediately is that the poles of the Green's function will give you a signal, capital psi, or the waveform at infinity, that's a sum over all the solutions omega of e to the minus I omega t, which I separate in a time scale tau. It depends on two angular numbers that we use to decompose to get rid of the angles, and then an overtone index n. Okay? It's a complex number. The other number gives you the ringing. Okay? So the waveform rings and attenuates exponentially. It rings down. This is why we say the signal is ringing down. The black hole is relaxing to the final state. Okay? So the idea is very simple. So you calculate these numbers, the frequency f and the timescale tau. We know them from linearized theory to 20 decimal places. You can really, I can give you notebooks for this. And the idea is going to the data and comparing and seeing how well it matches. Okay. If there's questions, let me know, please. Okay. Now, this exercise is done kind of daily with all the oscillators we know. For example, our sun also has proper modes of vibration. You can estimate them by, with the back of the envelope, 5-minute calculation. And you'll realize that, well, the sun is very complicated. So of course, these numbers are not very simple. They depend on a lot of things: the radial structure of the sun, the opacity of the material, the temperature of the star. But you can easily convince yourself that there's millions of modes, and the periods of these modes vary between 4 to 6 minutes. That's more or less the time scale that we're talking about for the sun, okay? The quality factor is an important number, and it tells you in that time scale, in the lifetime of the mode, how many times it rings, okay? For the sun, you get quality factors of 10 to the 6 to 10 to the 9. It's a really good oscillator. It rings down very well. And the reason why we can do heliosismology, why we can study the modes of the sun, is because they're being constantly excited by turbulence. There's nuclear reactions going on, and that's feeding the sun. So the sun is constantly oscillating in its proper modes. Okay?
So Vitor, these modes have been measured for the sun, or is theoretical?
Yeah. We've measured hundreds of modes for the sun, and there's a science called heliosismology, which even constrains physics beyond the standard model, because we know so well the sun. So if you try to change your theory of gravity or interactions too much, it's not gonna reproduce the spectrum of the sun. Yeah, it's a fabulous tool.
So what do you actually observe in order to, do you observe the brightness at different points on the sun, or?
Yeah, so actually all of this image are actually is an actual observation. Okay. The colors tell you whether the modes are red or blue shifted with respect to a star that's at rest. So what you measure is frequent. Of course you measure a time series. You Fourier transform. You'll be able to see hundreds of peaks, and each peak has a width, and that depends. That's the time scale. It depends on how you feed it turbulently, but you can relate that to all the spectrum of the sun. That's how you do it.
Thanks.
That's an excellent question. You can, in principle, do the same for the sun. Okay, meaning you take for a black hole. You take a black hole, like here, you're surrounded by an accretion disk. Most black holes out there in the universe have matter around them. And as the matter falls, it's exciting the modes of your black hole. The problem is that the amount of matter is so small that the excitation of gravitational waves of the modes of black holes is usually very weak. You need a very, very violent process, and that means, for most of the times, just black hole collisions between two black holes. That's really going to excite the entire space-time. Okay? And before I continue, let me show you the actual spectrum of a black hole. I told you that there's numbers that tell you the angular distribution of the modes. The dominant mode, we call it the quadrupolar. It has an index L equals 2. And if you focus on just L equals 2, so all the black dots here, if you start running the notebook or your routine to calculate the modes, you'll find an infinity number of them, okay? The most important is the one that has the smallest imaginary part, and then therefore it lives the longest. The time scale is the longest, right? So while all the other modes decay quickly, this guy is hanging on for a while. Okay, that's this dot over here. And you see all the dots, those are all solutions for the spectrum. For instance, if you plug numbers for a 10 solar mass black hole, it means that the black hole rings at around 1 kilohertz in gravitational waves. And the time scale, the lifetime of this mode, is 0.5 milliseconds. It's really a very, very short time scale, okay? The quality factor, the amount of vibrations in the time scale, it's really just a ratio between omega r and omega I, and you get a quality factor of roughly 3. If you think about the sun, the quality factor was 1,000,000. Black holes have quality factors of 3. They're terrible vibrators, terrible. And this is where all the difficulty, this is why it's so hard to use them, okay? That's why it's so challenging to actually study black holes with quasi-normal modes. Now, that was a linear analysis. We were just looking at the poles in the Green's function, okay? In the last few years, we realized that the story, that we need to understand really well the story, okay? If you actually are an observer sitting somewhere here, where my cursor is, okay? And there's a source, this planet or this star, waving around the black hole, then the observer is going to see 3 different sorts of signal that are encapsulated in the Green's function, okay? The first is a prompt propagation from source to the observer. That's the stuff we do when we look at flat space things, okay? The other one that we are calling the ring down or quasi-normal modes are excitations that were gravitationally lensed by the black hole. They approached the black hole very, very closely, okay? And they went around the black hole 1, 2, 3, a large number of times before hitting the observer. That's the ring down stage. But there's also a part of the signal that was actually traveling outwards, and it got backscattered by the geometry, by the space-time curvature. We call these delay time tails in the signal. And what I want to tell you is, at any instant, an observer is picking up all of this. Okay, that's important. That's something we learned, or we're learning, if you wish. Okay, there's not a clear separation. Life isn't that simple. Okay, and I don't think any one of us knows how to properly separate each of these components. We know it's there, and we know there's a stage in the life of black holes, this little guy over here, that seems to be dominated by waves, the ring down waves that were orbiting the black hole, okay? In fact, state-of-the-art numerical relativity, this signal over here, produced a few months ago, for the first time shows you all these 3 components. The prompt signal, this is really just the merger, the head-on merger of 2 black holes. You see the prompt signal, the ring down waves, the black holes merged, they left some gravitational waves orbiting the final guy, the observer is picking them up, and at late times, the ring down died, and what you see, what the observer sees, is waves coming from very large distances, okay? Good? Okay, now let's do spectroscopy. And by the way, Shahar, tell me to shut up when the time comes, otherwise I'll be here a week. So what we have to do is very simple, okay? We take a gravitational wave, this guy over here, and we're going to fit the signal with a series of exponentially damped sinusoids, right? And any of us knows, by the way, this is where all the difficulty has been in the past 5 years or so. Okay, the first thing we know is, obviously, we shouldn't be fitting to an exponentially damped sinusoid here. because the black holes have not even merged, right? So perturbation theory should not even apply. So maybe we should start here. But where exactly? Here, in this peak, in this one? Where exactly does ring down start? And I think the previous slide told you, well, there's no defined starting time, and there's no defined end time. So what the LIGO-Virgo collaboration did is, well, let me start fitting first at the very peak of this signal. That's when the two black holes coalesced. And let me see what I find. Okay. Now, what they found, so what they're going to show you is the 90% posterior distribution for the time scale of the mode and the frequency of the mode. And when you do it at the peak, okay, that's roughly this green line over here. It's 1 millisecond after the peak of the wave. The decay time and frequency should be somewhere here. And this is terrible because the black solid line shows you what you should actually get from the perfect numerical relativity simulation of that event. Right? From numerical simulations, you estimate the mass and spin of the black hole, you calculate the time scale and frequency, and the number should be here. Well, then, maybe we're feeding too early. Maybe this is still in the nonlinear regime, and we shouldn't be doing this. But if we repeat this 3 milliseconds after the peak, this purple line, now everything is good. And if you do it 5 milliseconds, everything continues to be good, and so on and so forth. Okay? So this is the first example in history where we're taking a gravitational wave and we're doing spectroscopy of black holes. You may look at it and you think, but this sucks. This is terrible. Look at the error bars. I mean, it could be anywhere here. But it's the first example. Okay? Unfortunately, the signal in the gravitational wave is so weak that we can only measure the dominant mode, one mode here, but it's still a perfect start as far as I am concerned. 2 years ago, a group reported that for one particular event, this event over here, GW 190521, you can actually start measuring two modes. And their procedure was kind of neat. They separated the analysis in two frequency windows. They were able to measure the quadrupolar mode, this guy over here. It agrees with the expectations really well. And then they measured the octupole, the L equals 3 mode. Okay? I'm not going to, well, you can actually see it here. You see that the error bars, again, are large. Okay? This is 2025. The signal to noise ratio that we're getting in ring down is 7. And for those that don't know what this means, it's roughly at the threshold between detection and non-detection. It's not great because of that. The future is going to look like this. This is a simulated event that we hope to get 10 years from now, where instead of having a signal to noise ratio of 7, it has 40, okay? With that, the same error bars that you saw there now becomes this. Really, really small. Again, it's time scale of the mode versus frequency. And you can even measure the second mode, and it doesn't overlap with the first, you see? So you can start testing general relativity. Why? Because curved black holes are defined by mass and spin. So if you give me the mass and spin, you calculate any mode, right? So you measure this mode, you can invert to find the mass and spin. You measure this mode, you can do the same thing. And if the estimates don't agree, you have a problem. The theory cannot be correct, or you did something terribly wrong, okay? So that's how it's going to be, I think, for the young people in the audience. 5, 10, 20 years from now, I hope this is what you'll be doing. You'll be testing Einstein by looking at the modes and saying something here is weird. The higher order modes are not agreeing with lower ones, okay? This is 40 LISA, the space-based detector, is going to see signal-to-noise ratios of thousands. You can't even plot that here. It's going to be precision physics right there. Now, there's a lot of challenges. I don't want to go over them, but there's a lot of things we don't understand. Okay, there's a lot of things we don't understand in the strength of the poles, how much each mode is excited. Can we do this from a first principle analysis in perturbation theory? It has not been done. We don't know how to reconstruct properly the time signal with a superposition of quasi-normal modes. We don't know really the role of environments. These black holes are not in vacuum. What happens if we put a black hole inside a galaxy or an accretion disk? What exactly is going on? Okay? And you need to worry about nonlinearities. You need to worry about the stability of the spectrum. You need to worry with a lot of things. Let me tell you one of the things that we learned in the last 2-3 years. And it came surprisingly from fluid dynamics. Okay? I was telling you that the poles, the quasi-normal modes, are poles of this function. Okay? But you can do something a bit more sophisticated, which is instead of looking at the exact pole, you look at the neighborhood of the pole. You're going to look at the norm of the resolvent, which is infinite at the pole. You're going to look all through the complex plane. Okay? When people did this in certain flows in fluid dynamics, they found something very interesting. Okay? This is what they found. This is the norm in the complex plane of this resolvent. And you quickly see that it's infinite. Well, it's not obvious, but it's infinite at the mode, at the quasi-normal mode, if you wish. But it's also extremely large, close to it, even in small vicinities of this. Okay? This is called, by the way, the pseudospectrum. The norm of this operator in the complex plane, we call it the pseudospectrum. And this is telling you that there's some instability going on. Even though the mode itself, the quasi-normal mode itself, is stable in the time domain, something funny is going on in the vicinity. And if you actually go to the laboratory, what you find is that this flow is not stable. It develops turbulence very close to this point. And that turbulence is well described by the pseudospectrum. It was an amazing discovery. Okay? Now, 3 years ago or 4 years ago, the pseudospectrum of black holes was first calculated, and it shows exactly the same signatures in the extremal limit. This is it. These are contour lines of fixed pseudospectrum, and it tells you that if the black hole becomes too extremal, it also develops this sort of instability. We don't know what it means. This is just a fact for you. I'm sure we're going to see a lot of developments here in the next few years.
Sorry, Vitor, can you explain exactly what's the signature of the instability in the extremal limit?
I don't know. So I tell you in the fluid dynamics, what it says is, even though a linear analysis says the fluid should be laminar, should be smooth, should be all okay, if you actually perform the experiment, turbulence starts developing before the linear analysis predictions. What is this telling us in the case of black holes? I am not sure. It is true that it happens mostly for extremal black holes, which we know also are prone to an instability. The so-called Aretakis instability, it's a near horizon phenomena. But we're far from having understood the meaning of all of this. It's just there. When you calculate the pseudospectrum, the lines branch off close to that pole. Okay.
Thanks.
So that concerned the stability. I think if I have 5 minutes, I'll still go back to that. But let me also tell you about the big assumption here, which is we started linearizing the field equations. Is this a proper thing to do? And if you start looking at how nonlinear the collision between two black holes is, you'll realize maybe we need to take some care in that, okay? So I plot here just for fun the luminosity, the energy per second, or the energy per unit time that we can produce with violent things. For instance, the Chinese dam, I think it's still the largest dam in the world, has a luminosity, again, energy per second, which is 10 to the minus 43 times Planck luminosity. Planck luminosity is this number over here, okay? Gamma ray bursts, that's V loves, they have a luminosity which is 10 to the minus 5 of the Planck luminosity. It's the largest thing we know in the electromagnetic spectrum, okay? But if you look at gravitational wave emission, when you throw two black holes at one another and they merge, the luminosity is up to 10 to the minus 2, 10 to the minus 1 of the Planck luminosity. It's a lot of energy per second being radiated. So you might suspect, how can this be linear? How can we think of the relaxation of two black holes in a linear way? Okay? Actually, we shouldn't. And so, well, recently, this is all the hype right now. Recently, we started looking at how to extend what used to be the linearized analysis to higher and higher orders. So if you expand the field equations, not to first order in the metric fluctuations, but to second order, what you'll realize is that your second order quantities, which I'm calling psi2, okay, they are described by exactly the same operator on the left-hand side, but they are sourced by the square of the first order guys, the guys that I've been talking about, okay? So what does this imply? Think about the relaxation stage, the ring down. There's characteristic frequencies. Psi1 at linear level is e to the I omega t, correct? The square of that should be e to the, well, 2 I omega t. This tells you that if you look at gravitational waves with enough precision, you should find 1, the linear modes, and twice the linear modes. That should be the nonlinear contribution to ring down. So 2 years ago, we started testing this to see if it was there, at least in simulations, okay? The idea was simple. We take two black holes, we throw them at one another, and we extract the ring down, the frequencies that are there in the spectrum, okay? We first remove, we find and remove the linear piece and search for what's there, what's left, okay? So what I'm plotting here is the amplitude of the nonlinear mode, the mode that has twice the frequency, as a function of the amplitude of the linear mode. Okay? If this is not clear, please let me know. And I'm showing you that amplitude for different center of mass collisions. Gamma is the Lorentz factor of these collisions. Two black holes colliding at varying energies, okay? And what you see is a beautiful, beautiful quadratic curve. The amplitude of the mode that has twice the linear frequency scales quadratically with the amplitude of the linear mode, as it should from this equation, right? The amplitude of the left-hand side should scale quadratically with this guy. It's, to my knowledge, the first very robust evidence that nonlinearities are there in the signal. You can quantify them. If you define the ratio, which is the amplitude of the nonlinear mode over the square of the linear mode, for the things that we expect to see, black holes in quasi-circular orbits, this ratio is of order 0.16. It's small. LIGO will not be able to measure it, but it's not hopelessly small. LISA and other detectors that will come in the future will be able to dig up nonlinearities in the signal. Really, I think this is an amazing time to be living. We understand even how the ratio depends on black hole spin. We understand how it depends roughly on initial conditions. There's a lot of things we don't understand. We don't know the large, what we call the Eikenau limit. We don't understand how or if we can resonantly excite these modes. We don't understand properly the extremal limit. So there's a lot of work to be done ahead, but it's exciting. It's another test of Einstein's theory that's coming there. Okay. Shahar, how much time do I have left?
Well, at least 20 minutes, but
Perfect.
yeah.
So this concerns the vacuum case, linear and nonlinear regimes. This is all fine. As I told you, black holes, well, nothing is in vacuum, okay? Black holes live around galaxies, they live around dust, accretion disks, whatever. So you might ask, what happens to the spectrum of black holes if I actually put some things around it? Okay? So we asked this question as a community. Well, we've been asking the question because what we found is very surprising, okay? And we are very ignorant on how to model black holes in the real universe. So what we've done was something a bit too crude. Let me tell you what we did and what we find. So we modeled whatever matter is out there by a small change in their effective potential. You know, let me go back to that. So the linearized equations is governed by this thing over here with some effective potential, okay? That effective potential looks like this. It's V as a function of some radial coordinate. It peaks close to the black hole. The units are not really important, but that's it, okay? And if there's vacuum, all of this goes down as 1 over r squared. We understand it beautifully, okay? So the question we asked was, if we place this black hole close to a star or close to something else, the effective potential is going to change, okay? It's going to depend on whatever you put there. So let me assume that what the matter does is to create a small bump. Can you see this inset? It's a small bump. The amplitude is very small. I'm going to put it a millionth. So this amplitude epsilon is going to be a million times smaller than this amplitude. It's supposed to be really small, okay? And I'm going to put it some distance a away from the black hole. That's what we're going to do. And then we're going to take our routines and we recalculate the spectrum of the black hole. I hope this is clear what we're doing. We're just slightly changing the potential and we're recalculating the quasi-normal frequencies, okay? What we find is this plot over here. So we are going to vary A, okay? This solid black curve tells you what happens. I start with vacuum, this dot over here, and I find the modes in this complex plane, the imaginary part and the real part, okay? Now I start increasing A. I start at roughly 30. Now here it's at 40. Here it's at 45, 50, 55, and so on. Epsilon was set to 10 to the minus 6. So it's really a small bump, okay? But you see what's happening. A small bump, which is a million times smaller than the main guy, the big black hole, is changing the frequency by, well, it was 0.18 here, it's 0.1 here, by a factor of order 2. This is unbelievable. In fact, when people started doing this, they thought there was a problem in the numerics. How can it be? How can a flea, how can, I don't know, a small star, dust, a grain of dust that I'm pushing farther and farther away from the black hole? You see, I'm pushing the bump away from the black hole, and the modes are getting more and more distorted. It's ridiculous. How can we even trust what LIGO is giving me if it's so sensitive to matter, right? So this problem is called the elephant and the flea problem. The elephant, of course, being the black hole, the flea being the small bump you put there. And it was known, actually, the name was given in quantum mechanics because exactly the same thing happens there. Now, what we understand now is that the calculation is correct. The spectrum is totally changed. But what a detector finds is something, well, more intuitive. Let me show you the real-time signal of this strange space-time with a bump, okay? So what I'm doing here for you is I'm taking the black hole, I'm putting the bump, and I'm throwing a star at this black hole, and I'm looking at the gravitational wave signal, okay? Black line is the pure vacuum. There's no bump, there's no nothing. I just threw a star, and what you see, well, I think more or less you see, is the gravitational wave amplitude falls down exponentially. We call this the ring down, right? An exponentially damped sinusoid. And then you see what we call the tail. That's fine. Now, when you put the bump, and I'm placing the bump at a distance of 30 Schwarzschild radii, it's high, okay? It has a large amplitude, 10% of the main guy, but just so you can visually see what's going on. The star collides with the black hole, and what do you see? Well, you see a ring down that's indistinguishable from vacuum. Okay, that's what you see initially. And then, at later times, you see these weird revivals. Okay? So at very late times, the signal, in fact, is very, very different from vacuum. Now, let me tell you what's going on here. Because LIGO, or future detectors, they can only sense the wave when it's high amplitude. So they will only be sensitive to the initial stages. And there, the difference is practically zero. What's going on? The bump is creating a cavity, right? There's the large vacuum bump, and now you created this guy, artificial guy, supposed to be describing matter, some distance away from the black hole. Now you throw the star generates gravitational waves. They travel outwards, but you see, they see this bump. So the low frequency component of the signal is unable to tunnel out, if you think about quantum mechanics. It cannot tunnel out of this barrier, so it stays there. It stays there, it reflects, it comes backwards, but it sees the big bump there. Well, it can't tunnel. So it goes, you see it's sloshing back and forth in this cavity and slowly, slowly, slowly tunneling out. It's as if you have the gravitational wave in a room whose walls are semi-permeable. See, yes?
Yeah, what is exactly the shape of the perturbation? Is it spherical or is it just a point-like perturbation?
A point-like perturbation. You mean this, yeah, in this case, the point-like perturbation.
And what is the mass, epsilon equal 0.1? What kind of mass ratio does it correspond to? Is it 0.1 of the black hole mass, or is it?
Oh, no. This epsilon, this is a very artificial construct. It could mimic a mass of the order of the mass of the black hole. So it's not even a perturbation.
So you don't expect, suppose that you have a Emery in LISA with a small mass black hole with a small star falling in, and then you have another star which is nearby. It will not give you such a large signal.
I don't expect, so that's a very good, first of all, I don't think we know the answer fully. We don't understand, we don't expect matter, for LISA matter to give rise to this second guy, which is this big. But what I want to argue is that this is always going to happen. I hope I can make a good argument for that. Whatever matter, but let me go, but first let me just finish this part. what's happening is there's waves being trapped between the black hole and this bump. So at late times, you see, at very, very late times, what you see is the ring down of the cavity, not of the black hole. This is why it decays so slowly at late times. And when you do a quasi-normal mode calculation, that's what you're doing. You're finding the dominant frequency. So you're going to find this guy, this number over here, but it doesn't mean it's actually governing the time signal. Okay? And so now going back to what Zvi was asking, let me argue that this is a very, very general phenomenon. If you take a guitar, a simple instrument like a guitar, and you place it inside of a concert hall, just to make the case, exactly the same sort of physics is going on, right? You calculate the modes of the guitar in vacuum, you find some number. Now place the guitar inside the concert hall and calculate the modes of the composite system. They are totally different because you need to be aware of the boundary conditions at the walls of the concert hall, right? And yet, the time domain response when you actually pluck the guitar string is going to look like this, at least initially. Then at late times, the guitar strings couple to the air in the room, and then you're going to be sensitive to the walls there. So this is a very generic phenomena. We expect that, that our universe is kind enough that the matter is diluted and it's far away. So this portion of the signal will kick in at late times and with a low amplitude. But that's it. I mean, I don't think we are terrible, at least in my community, at modeling black holes in astrophysical environments. So we need to do much better than what we have done so far. Okay.
But Peter, just another question about this. Is it possible that if you take a small enough value of epsilon, so this behavior, this late behavior governed by the very weakly damped quasi-normal modes will actually be weaker than the power law tail, and then it won't govern the signal at any time?
No, because that only tells you, that's a good question. It's possible that in the real-time domain signal, yes. But you see, this calculation here doesn't know about amplitudes. It only calculates spectrum. And whatever small epsilon you give, it has an exponential sensitivity to the distance at which you place it from the black hole. It depends exponentially on the distance A. That's
right,
a real problem.
I was asking about the in real time. I mean,
oh yeah, it's true that if you do it in the time domain, it's possible that the amplitude of this guy is below the tails. That is possible. But it's also true that this decay is usually extremely small. So you really need a small epsilon to do the trick. Yeah, that's possible. Okay, now I was saying we are terrible at modeling black holes in environments. Let me finish my talk by telling you progress in this in the last, year or so, okay? I'm going to try to understand what happens when I place a black hole, this guy over here, of mass m, inside, I'm going to call this a galaxy, but actually it's something, a matter distribution with mass that can be 1,000,000 times more massive than the black hole itself. It's a non-trivial problem from the point of view of technical calculations, of calculating the gravitational wave response. Because when you linearize Einstein field equations, you also have to linearize, you need to perturb the matter. So you're going to have matter waves that couple to gravitational waves, okay? You can do it. There's a very interesting construction called the Einstein cluster, because Einstein thought about it. Actually, Einstein worked out the details. The idea was very simple. He modeled a galaxy by stars on circular orbits, but moving in all arbitrary directions. Okay, so all the stars in galaxies are having circular motion around the center, but with a direction of velocity that goes randomly. Effectively, this is equivalent to a fluid that's totally anisotropic. Only pressure, only tangential pressure. And if you work out the field equations, it really simplifies the problem a lot. Okay? So when you calculate, when you do exactly the same thing, you throw a star at a black hole inside this galaxy, at least this proxy for a galaxy, you're going to find the following. K, this black line over here, are metric fluctuations. The gray lines are density fluctuations, okay? And what you find is when the star crosses the black hole, actually the light ring of the black hole, you see the ring down excitation, the black hole ring down excitation. And because gravitational waves couple to the fluid, you actually see it here as well in the matter, in the density waves. Okay? But at late times, actually, now you see, you set the fluid of the galaxy in motion. You have matter waves crossing the galaxy, very low frequency waves. They couple to gravitational waves, and you also see it in the gravitational wave spectrum. This is another example of how the vacuum spectrum of black holes is easily destabilized when you couple it to matter. It doesn't really matter how low the density of the galaxy is. You're always going to find these modes there. They may have a very, very small amplitude, but they will be there in the spectrum, okay? So I think that's the lesson we learned. Spectral instability, this elephant in the flea is very general. It's always going to be there. We also learned we need to model black hole systems a lot better than what we're doing now. We're very naive in the way we're modeling black holes. Now, I promised I would tell you about the evidence for black holes. I think basically I told you already, but let me explain why, okay? The evidence for black holes in gravitational waves it's a 5-minute calculation to calculate the compactness of this, to estimate the compactness of the objects in the first LIGO event, okay? And the argument that you hear still from a number of colleagues is this has to be a black hole. Look at the signal. It's damped so quickly that the only thing in the universe that can do this is a black hole. There's nothing else that can do this, okay? And again, to make my point, take a star, this red dot over here, you throw it at a black hole. This is the effective potential it sees, and you generate this curve. This is the gravitational wave amplitude as it crosses the light ring. But now you also understand that you can easily mimic this signal without a black hole, right? Take the bump that we just discussed. It was placed far away from the black hole. Take that bump and place it very, very close to the horizon, extremely close to the horizon. Do away with the horizon and put there some structure, a wall, that's placed really, really close to the horizon. And you see the beauty of it is you're going to get what I just described. Prompt ring down, and at late times, at very late times, you should start probing the structure of the object you have there, okay? This is one example. I'm scattering a star. Black curve is black hole. The red curve is some wormhole, some weird object I put there, okay? You see, early portion of the signal is indistinguishable from a black hole. At late times, the gravitational wave that you generated, a fraction went in, it interacts with the object you have there, it comes out, and then you see it. But there's a travel time. It's a beautiful phenomena, right? Let me tell you what's going on in general. You have your main burst. This is how searches are now ongoing in the LIGO-Virgo-Kagra collaboration. You have your main burst, your main signal, we expect it to be the same for any object that's sufficiently compact, whether it's a black hole or not. Okay? But if you're patient and you have a good detector, after the main burst, you're going to see echoes of the main signal because the waves are trapped in that cavity. Now the cavity, you see, is the light ring and something close to the horizon. So you can parameterize your signal by a relative amplitude A between the burst and the first post-merger signal, and the time delay between the different echoes. Okay? There's a substantial number of analyses of the LIGO, Virgo, and also the Kyber collaboration. The best we can do is to exclude these parameters. Okay, this is the exclusion plot of gamma, this damping timescale, and the relative amplitude A. We haven't seen any evidence for echoes out there, or at least no robust evidence. I think detectors like LISA, Einstein telescope, or future detectors will either rule out a very significant portion of parameter space, or then see new physics. Maybe we will see post-merger signals, and you'll have in hands something that you need to explain from first principles. Okay, whatever happens, I think there's wonderful times ahead. So let me close by saying black hole spectroscopy has begun. It's not yet a mature field because there's a number of things to understand, but we have the data. We have the data and we know roughly, we have a plan regarding what to do with that data. The relaxation stage of compact spacetimes inform us on the final state conjecture. Is it true that we're going to be left with a curved black hole, a spinning curved black hole out there? Is it true that there's an horizon, or there's going to be some near horizon structure or environments that I can test with black hole spectroscopy? And it's not true that the signal is linear. I think this is something that many of us repeated for 20 years. And there was some hand-waving argument that the horizon and the light ring were filtering nonlinearities. It's not true. Okay? You might argue, and you should argue, why are we doing this? Why are we focusing on the late time, whatever? We have the full waveform. We have numerical relativity. Let's just do that. I want to stress that's exactly what we're doing, but we're dissecting every part of the signal. We are trying to make sure that we understand the physics involved in each component of the signal we look at. It's I think a wonderful time to be doing this sort of physics. We also learned that environments, they are important to understand. They are always going to destabilize the spectrum. They're also going to give you redshifts in the waveforms, but there's a much more work and creativity that I think we need in the field for this. Finally, echoes in post-merger signals are a general feature of near-horizon physics. You don't need fine-tuning for that. Whenever you change the space-time close to the black hole, the likelihood is there's going to be some echo in the gravitational wave. Let me tell you an extreme example that Bekenstein and Muhanov, well, they didn't predict it, okay, to be clear, but let me tell you something that happens in their kind of scenario. They were trying to quantize the black hole area spectrum because it's some sort of adiabatic invariant. Their proposal was that the black hole area comes in certain units, which we parameterize by some constant alpha, supposed to be over the 1, and the Planck length LP squared. Okay? So the area of a black hole would be some integer number n times this guy. If you accept this proposal, it's a very simple proposal. The rest follows. The rest is make some process whereby the area of the black hole changes. Well, we know the relation between A and N, so there you get. A variation in area gives you a variation in the mass of the black hole, because area is 4 pi times the horizon radius squared. Okay? Now compute the energy of the graviton that's involved in this process. Well, you know the delta M. The energy is simply the Planck constant times the frequency. So you get the frequency. It's this number over here. And alpha over 32 pi c cubed over the mass of the black hole, Newton's constant. The surprising thing, I think the outrageous thing actually, is that if you plug numbers, this frequency, if alpha is over the 1, is in the range of LIGO. This is exactly on the sweet spot of LIGO. So this is telling you that in this kind of range of proposals, which of course you should dispute, is this really the way that black hole area is characterized? But if it is, then certain processes involving black holes should not occur because the energy of the graviton is not enough, right? If the frequency of the graviton is smaller than this, they would simply not absorb. It's like you do away with your eyes and you put some structure. So you're back in the echoes thing. You should be getting echoes of some sort out of this area quantization. Okay? And I think I'll finish here. Thank you so much. I'll take questions, of course.
Thank you, Victor, for a great talk.
Thank you.
All right, let's.
Can I ask something? In future black hole spectroscopy using LISA, is there specific types of events that you are expecting to be more prominent for detecting beyond general relativity? Also, how is the features of the binary, like spins and mass ratio, will affect the waveform going down?
That's a very good question, Shani. So I think there's two things here. The expected changes to general relativity, and I think I would put expected in quotation marks, are always curvature corrections, right? You could write down something that looks like a Taylor expansion around GR, around general relativity, and these would have corrections in curvature, meaning objects with large curvature would make an impact, objects with small curvature would make a smaller impact. If you take this point of view, then LISA doesn't have anything interesting to say because it's going to see supermassive black holes and the curvature close to the horizon of a black hole scales like an inverse power of the mass. So large black holes, very small curvature. Okay?
Okay.
But this is only one proposal or one example of how you can change GR. There's many others. One of them is that you start adding light fields, light degrees of freedom. Light degrees of freedom have large Compton wavelengths. And if you take this approach, LISA is wonderful because it complements what LIGO can see. LIGO can see kilometer scale wavelengths. LISA would see million or billion of kilometers, right? For instance, if you want to constrain the mass of the graviton, LISA will do much better than LIGO, or yeah, substantially better than LIGO. Regarding spin, usually spin helps in anything you want to do. I think that's kind of the lesson. In the last 3 or 4 years, actually, we learned something somewhat strange. There's been 2 works that show that semi-classical corrections kind of diverge in the extremal limit. We don't understand very highly spinning black holes from a semi-classical perspective. So quantum impact reaction effects in really, really rapidly spinning black holes is supposed to be extremely large. Okay, so that's a natural place. Unfortunately, they need to be spinning so much that I'm not sure there's a mechanism in the universe that's able to spin them up to that value. Yeah.
Okay, thank you.
All right, any more questions?
Yeah, I have another question. Many years ago, Press and Tucholsky worked out what they call a black hole bomb, in which actually they were considering not gravitational waves, but, if I'm not mistaken, electromagnetic waves propagating between the black hole and the surrounding ring of matter or sphere of matter. And there are several versions. So and basically they were using the Tucholsky equations. They were solving the Tucholsky equation. Now, my impression is that the work that when you're discussing gravitational perturbations of black hole, then you're also solving the Tucholsky equation, but you're solving it for spin equal 2 rather than spin equal 1. So how are these two lines of work related?
Yeah, so I think they're related. That's a very good question. I had a slide on some of that. So the black hole bomb is basically the idea that you surround a spinning black hole with something that perfectly reflects radiation. Spinning black holes amplify radiation, and therefore you see that if this amplified radiation is forced to go back, it's going to be amplified again. So you find a way of extracting all the energy away from the black hole, right? The formalism they used and all the calculations is identical to what we've been doing. We don't think that the black hole bomb is going to materialize with environments because there's always leakage. Even if you place this bump, there's always leakage that's much more important than the amplification at the horizon. But for instance, the black hole bomb, so this was the 70s, in the 2011s or 14s, we realized that exactly the same mechanism can be used to grow massive fields. Massive fields is a perfect example of the black hole bomb. You remove the energy of the black hole and you place it in a light field outside of the horizon, and that relates to my answer to Shani. But I think there's another spin-off of that idea, which is whenever we start changing too much the horizon structure. For instance, if we remove the horizon of a black hole, then a sort of a black hole bomb is going to appear. If I have a spinning object with an ergo region but no horizon, if you work out the Tucholsky evolution for this object, this guy is going to spin down very fast because he's going to amplify energy and get stuck with negative energy states in the ergo region. So it's kind of a spin-off of the black hole bomb idea. Yeah, but the formalism is exactly the same.
All right. Any further questions? Okay, if not, let's thank Vitor again.
Thank you so much. It was my pleasure.
Vitor.
I hope to see you all soon. Bye-bye, Sean.